Next section is going to be about what are called trigonometric equations. It's Unit 5, Section 5 in the book. We'll do this in two parts. First part today, we're going to look at ones where we find all real solutions, and we say all real solutions because you need to remember that these functions are periodic, meaning they repeat themselves. So one thing, sine and cosine repeat themselves every 2 pi, and tangent repeats itself every 1 pi. Okay, those are going to be the important ones to remember for this. And in particular, we're also going to use these when we start talking about an interval. And usually that interval is going to be between 0 and 2 pi. So things you're definitely going to need when we go through this unit are your unit circle and your identities notes. More particular, you probably won't need your identities notes for this lesson, but for part 2, you're definitely going to want them for that because there's going to be times we're going to need to apply our identity notes. Biggest thing when we talk about trig equations, again, stuff that we've been struggling with so far, is we are going to solve our trig equations just like an Algebra 1 equation. So an example of that would be if I tried something like this. 5x equals 3x plus the square root of 3. Same way we've always done it. We need to get our x's on one side. So I'm going to subtract 3x from both sides. That's going to leave me with 2x equals the square root of 3. And now to get x by itself, I divide by 2. And so x would be the square root of 3 over 2. And that would be your solution for this equation. Hey, when we do trig equations, because our functions are periodic and because they do repeat themselves, to do all real solutions for sine and cosine, when we solve for our angle, now that doesn't mean that we're completely solved for the variable, but when we do it for the angle, we're going to have to add 2n pi to any angle that we find. So angle plus 2n pi. We may then have to go further to solve for x, and when we do tangent, we're going to have to take whatever angle we find using our unit circle plus n pi, where n is just going to be some integer. So essentially we're saying we're just adding some multiple of 2 pi here, and for tangent we're adding some multiple of 1 pi. An example of what that looks like, just like the algebraic equation I just showed you, what we're doing here, same idea. Think of your trig function as an entire variable. So instead of subtracting 3x like we did before, we're going to subtract 3 sine x from both sides. Same idea, we want to get our trig function on the same side in this case. So we'll have 2 sine of x equals square root of 3. It's looking very similar to that one we did before. Same idea, divide both sides by 2, and so sine of x equals the square root of 3 over 2. Okay, here's where we need to look at your unit circle. And we need to remember that sine tells us to look for the y value. So we want to say x, what is our angle, which is what x stands for. What is our angle when our y value is square root of 3 over 2? Well, if you look at your unit circle, you see it is at pi over 3, but it's also at 2 pi over 3. Okay, so we don't need to worry about the domain restrictions we had before because we're talking about sine, not sine inverse. But, and this is where that last slide comes in, because we're repeating every 2 pi, we need to add in 2n pi to both of these angles. Okay, and now x is solved for, so we have we have an infinite amount of solutions because we're repeating every 2 pi, but we have 2 angles that we're adding 2 pi to. Okay, now one that would make it just a little bit more complicated is if we look at this. And a lot of times we want to get rid of that 3 first, but you notice the 3 is inside your tangent function. It's really tangent of 3x. 3x is your angle. So what we need to think about on a unit circle, when is tangent, or our y over x, when is our y coordinate over our x coordinate equal to 1? Well, that's going to happen at pi over 4 and also 5 pi over 4. So that means our angle from this problem, 3x, is equal to pi over 4, or our angle from this problem is 5 pi over 4, but remember that previous slide we talked about, we have to add n pi to each of these because that would be how long until the period reproduces itself. This is the one where I was talking about where we have to do a little bit more work because x isn't by itself. So we're going to divide both sides by 3. Remember, dividing by 3 is the same thing as multiplying by 1/3, so we'd end up with pi over 12 plus n pi over 3. That is one set of infinite solutions. The other one, dividing by 3, we'd end up with 5 pi over 12 plus n pi over 3. This would be your two sets of infinite solutions. And I know that's a little bit complicated. Again, we'll talk a little bit more about tomorrow about why we're adding n pi and why we're adding 2n pi if that's what's confusing you. So really what we found so far is an infinite set of answers. If we restrict our domain or restrict our solution, usually you're going to see something like 0 to 2 pi. Then we're going to need to test values of n. So we're still going to be adding that 2n pi if it's cosine or that n pi if it's tangent. You're going to plug in values for n. So you're going to say n equals 0, n equals 1, n equals 2, until we are no longer in that solution set. An example of that, so you see here we're talking from 0 to 2 pi. First thing, again, remember this x over 2 is the angle, so we need to get rid of that sign first. So the angle, the y value, square root of 3 over 2, is pi over 3 plus 2n pi, or the angle x over 2 equals 2 pi over 3 plus 2n pi. Okay, and now we need to continue to solve for x. So I'm going to multiply here both sides by 2. I'm going to end up with 2 pi over 3 plus 4n pi, because I multiply both of these terms by 2, and likewise I do the same thing over here, so 4 pi over 3 plus 4n pi. Okay, now if I move these over just so they're a little bit closer together, okay, they are two different things. This is the case, since we're talking about just the interval 0 to 2 pi, we need to test values of n. So if I plug in n equals 0, well, the first one I just get 2 pi over 3, and the second one I get 4 pi over 3. Both of those are in that interval, so we're good. We need to check n equals 1, but if we check n equals 1, we get 2 pi over 3 plus 4 pi, because 4 times 1 is 4, plus pi. This one won't work, so we don't need to go any further on that one. And likewise, if we check over here, 4 pi over 3 plus 4 pi, well, this is already outside of 2 pi, so we know that that one doesn't need to go any further. Okay, it's just a coincidence that our first test is the only one that worked. Usually, problems that we choose are going to have n equals 1 and maybe even n equals 2, depending on what our angle here is. Okay, so that's the big thing with this lesson. All real solutions, you're going to have to add 2n pi if it's cosine or sine. You're going to add n pi if it's tangent, or, well, tangent is all we're going to worry about. And then for on a given interval is when we need to plug in n equals 0, n equals 1, and on down the line until we have found them all inside that interval, which is usually going to be 0 to 2 pi. Okay, we'll see you next time.